So, now we are going to talk about jointly distributed random variables. See, there may be events which need to be described by more than one random variable. So, there may be the phenomena, the random phenomena concerned with the event are more than one dimension, and therefore, we need to be able to of course, then we from 2 dimensions we go to multi dimensions also, but right now to keep it simple we will first talk about 2 dimensional random variables and then maybe extend the notion to more than 2. So, if x and y are 2 random variables, we define their joint cumulative distribution function as follows. So, probability so f of x less than or equal to a comma y less than or equal to b is actually the probability that x is less than or equal to a and y less than or equal to b, a and b 2 real numbers between minus infinity and infinity, right. Okay, so, essentially in this diagram your if this is b, then you are asking for y less than or equal to b and then x less than or. So, it will be this whole region, right. If you can see this line and this line. So, whole of R 2 extending from here to this end, right. That will be your you are talking of the probability over this region. Okay. Then the moment you define the joint CDF, the cumulative distribution function, then you can talk of the marginal CDF. So, for example, of marginal CDF of x can be obtained from FAB as follows. Oh, sorry, this should be AB. The probability part comes here, x less than or equal to a, y less than or equal to b. So, therefore, from FAB we can obtain the marginal CDF of x as follows. So, this is fxa, which is probability x less than or equal to a. So, this will be actually, therefore, that means this means that y is allowed to take any possible value. So, therefore, y probability x less than or equal to a and y less than infinity. So, now let me just define it in a proper way, in the sense that this is also the same as b going to infinity. So, limit, that means if I take the event x less than or equal to a, y less than or equal to b, and then I take the limit. So, you see what will happen as b goes to infinity. So, x less than or equal to a, y less than or equal to b, you are talking of this. Then when say b 1, then you talk of this y less than or equal to b 2, where b 2 is greater than b 1. Then this is a bigger event, right. This event is contained. So, therefore, now you have a sequence of these events which are increasing. So, increasing sequence of events as b goes to infinity. And if you remember my definition of probability as a continuous function, continuous set function. So, then in that case I told you that we can in that case extend, I mean when you have an increasing sequence of sets, then and you are computing the probability, you want to take the limit, then the probability of the limit is the limit of the probability. So, therefore, I can take limit outside and this will be limit as b goes to infinity of the this event x less than or equal to a, y less than or equal to b. So, you take the probability here and therefore, this will be limit and this is now your f a b by definition. So, this limit b going to infinity of f a comma b and this will be then f a comma infinity. So, f a and f a comma infinity are the same. Similarly, if you want to compute the marginal of y, then we will take the limit f a comma b, a go to infinity, a go to infinity, which will be f infinity comma b. So, exactly in the same way we will argue out that the b remains the same and then a keeps increasing. So, again you have increasing sequence of sets, and so when you take the probability I can I can exchange the limit and the probability and get the answer. Okay. So, now similarly you want to compute and then of course, you see the properties that we had defined for that cumulative distribution function must have for a single variable. So, the same will apply and you can apply them to f x and f y. So, through those you can get the property for the joint right, because the property that f x and f y possess, combine them and you can then put together the properties that your joint cumulative distribution function must have. Okay. Now, suppose you want to compute the probability of x greater than a and y greater than b. So, this we can write as 1 minus probability of the complement of this event, which is x greater than a, y greater than b, a complement. And then since x and y are independent, in the sense that I can write this as now this can be written as x less than or equal to a union y less than or equal to b, right, from if you recall your De Morgan's laws and so on. So, then this will be 1 minus probability x less than or equal to a minus probability y less than or equal to b, and then you add probability x less than or equal to a comma y less than or equal to b, and this diagrammatically also you can immediately see that this is how from here we have to get here, because you are computing the probability x less than or equal to a and y less than or equal to b. So, this will be, you see, x less than or equal to a would give you this region, right, and y less than or equal to b will give you this region, right. So, you see the region extending from here, x less than a, y less than b is this region, which you have subtracted twice, because once when you do it for x less than a, probability x less than or equal to a. So, it is this. So, then this region is coming into it, then when you subtract probability y less than or equal to b, then again this whole region is coming, right, and therefore, you add this again. So, in words of your, I should have written this, that means your yeah. So, therefore, I will simply write this probability in terms of 1 minus f x a minus f y b. So, this will be equal to 1 minus f x a minus f y b plus f a b. So, therefore, to make the equation correct, I add this once, and then because I need to subtract only, see, I need this region. So, the valid region that I require is this, and therefore, from 1 I subtract this whole, and so this got subtracted twice, therefore, I add it once to make it proper. Okay. So, this will be your that means, now one can compute whatever probabilities you want related to these two random variables. It can be done once we have made this definition. Now, in general, if x is lying in the interval a 1 comma a 2 and y in the interval b 1 comma b 2, then this can be written as f a 2 comma b 2 plus f a 1 comma b 1 minus f a 1 comma b 2 minus f a 2 comma b 1. So, here again we will just simply diagrammatically look at the equality that we have here. So, x is varying between a 1 and a 2 and y is varying between b 1 and b 2. Then f a 2 b 2 is this whole area, right. In fact, if it's not if it's only non-negative variable, then it is this region. So, just assume for argument's sake that this is both the variables are non-negative, but otherwise it will extend to infinity and this will extend to infinity. So, anyway, because this is f a 2 b 2 is probability x less than a 2 and y less than b 2. So, in the case of non-negative variables, this is the total region. Then f a 1 comma b 1 is this region, let me this here. Then f a 1 comma b 2, a 1 comma b 2 is this whole thing, and f a 2 comma b 1 is this region here. So, you see that here you are subtracting this region twice, and in this a 2 plus b a 2 comma b 2 you are adding it and then you are adding this. So, that gets cancelled out and this region also gets cancelled out. So, from the whole of f a 2 comma b 2 you are finally left with this particular region. This is the idea. I am equating the probability with the area in a sense, right, and that is how I am trying to explain. Okay. So, if you keep this picture in mind, then you can always make the right computation. Now, in case x and y are discrete random variables, the joint mass function can be written easily. because here you are simply wanting to compute these probabilities. Probability x equal to a, y equal to b is p a comma b. This is how we will define. So, if we can compute this probability, then that is the probability a comma b, and this for all possible values the pairs a comma b taken by x comma y. Okay. And then we can also compute the marginal probability mass function of x, which will be simply probability x equal to a, and this will be your summing these probabilities over. So, fix the x at a, and then you are summing it over all possible values of y. So, you are summing up p a comma y for all possible values of y, that will give you the probability that x attains the value a, because here the value of y is immaterial. So, therefore, you sum it up over all possible values that y will take. Similarly, p y b will be summing up these probabilities x comma b when p x b is positive. Right. So, in this case you want to sum up over all possible values of x to get the probability that y will take the value b. Right. And we will go through an example here. So, let us consider this: 3 balls are randomly selected from an urn containing 2 red, 3 white and 4 blue balls. So, the total number of balls is 9, and now you want to find the joint distribution function of x and y when x and y when where 3 balls are chosen from the urn and x represents number of red balls and y number of Okay. So, I pick up 3 balls from the urn, then I note the number of red balls present in those 3 balls and the number of white balls. So, now we want to write down the joint mass function or distribution function for x and y. So, let us now continue with the example with which the urn contains 2 red balls, 3 white and 4 blue. Total number of balls is 9. So, you want to compute the cumulative mass function for the variables x comma y, where x is the number of red balls and y is the number of white balls when you pick up 3 balls from the urn. Right. So, let us I will just compute a few and then you can try to complete the table. I think maybe I have completed it already. So, when you want to compute the probability of 0 0, that means x is equal to 0 and y is 0. So, which is no red ball and no white ball. So, that means all the 3 balls that you pick up from the urn must be blue. So, the probability of all 3 balls being blue is 4C3, and the total number of ways in which you can pick up 3 balls from 9 balls is 9 choose 3, and so this number comes out to be 1 upon 21, which is here. Right. Then I should have computed P 01, and I think I have written it here as so it's this number is actually okay. So, it's got mixed up. Okay, this is 1 by 7. So, that's okay. Probability 1 by 0 is 1 by 7. So, if you want to compute, have I done it somewhere here? No. So, therefore, let us just quickly compute this number P 01. So, 01 is probability no red ball and 1 white ball. Okay. So, this will be no red ball, that means 1 white ball and 2 blue balls. So, blue is 4C2 and 1 white out of 3. So, this is 3 choose 1 divided by 9 choose 3. Right. So, let us quickly compute this. This should be 6, 3, and then from here you will get a 6, and this will be 9 into 8 into 7. Okay. So, 6 3s are 18, and this will be so twice 4, then 2 and 3. So, this is 3 by 14. So, 3 by 14 is this. Okay. So, 3 by 14 is this number, right, and this way I have made some computations. So, 0 2 you have to compute and so on. So, I have shown you some computations here P 1 2, then P 1 0, P 1 1 we have computed, and so you go on. So, now the whole idea is that once you have completed this, then as I was saying that if you want the marginal distribution for x, then so for example, if you are looking for the probability, let me just take it off from here. So, if you add up the numbers here, this is what probability x equal to 0, then you are giving values to 0, 1, 2 and 3, right. So, in other words, you are adding up probability, let me write it as 0 0 plus probability 0 1 plus probability 0 2 plus probability 0 3. So, there can be 3 white balls, because total number of white balls is 3. So, all this will give you the probability that x is equal to 0, right, because when you pick up the 3 balls, if it does not contain any red balls, then those 3 balls will either contain no white ball, 1 white ball, 2 white balls or 3 white balls. So, all these probabilities add up to the probability x equal to 0, and so this will be right. Similarly, when you add up the second row, that will give you probability x equal to 1, third row will give you probability x equal to 2, and this will be probability x equal to 3. But since this is all 0, because there are no the number of red balls is only 2. So, you can't have number of red balls in the sample that you pick up as equal to 3, right. So, therefore, this is all zeros. Similarly, here you can't have the combination 3 comma 3, because you are picking up only 3 balls, and similarly 3 comma 2, 3 comma 1 is also not possible. From here 2 comma 2 and 2 comma 3 is also not possible. So, these are the only numbers, and you see this now finally, because this is probability x equal to 0, probability x equal to 1, probability x equal to 2, which are all the possible values that x can take in your sample of 3 balls, right, because there are only at most 2 white balls that can appear in a sample. So, this must add up to 1, and similarly when you add up, see when I add up these probabilities, this will give me the probability that the y is equal to 0. That means, there is no white ball in the sample. When you add up these numbers, this will give you the probability that y is equal to 1, right, and similarly this. So, all these 4 when you add up, that should also add up to 1, and that will give you a good check. So, again that means, when we are defining the marginal PDFs and so on, then we must continue to check the validity, right, and so make sure that your calculations are okay, because otherwise you will know that you have made a mistake somewhere. So, you can go back and check. So, all these numbers, so the numbers here will give you the marginal distribution of y, here the numbers will be marginal distribution of x and so on. Okay. So, this is how you write down the joint probability distribution of 2 random variables. Now, take another example. So, that I want to make sure that you understand how the calculations are being done. Now, this is an example in which there is a community in which 15% of the families have no children, 20% of the families have 1 child, then 35% of the families have 2 children and 30% have 3 children. Now, the probability of the children being a boy or a girl is same. That means, it is half. So, once you pick up a family at random, so the experiment that we are doing here is that you pick up a family from the at random, that means, any family is equally likely. Then you want to find out the number of boys and girls in that family. So, both of them are random variables. That means, number of boys in the family and the number of girls in the family that you have picked up at random. Okay. So, here again let us see, I have made a few calculations. So, if you want to compute P 0 0, then that means no children. So, of course, this is straightforward, you know that 15% of the families have no children. So, this is simply 0.15. So, which we write here. Then when you want to compute P 01, that means no boy, just one girl. So, this is the event, probability of one girl child. Now, I will write this as a conditional probability, saying that probability one child into probability one girl, given that there is one child in the family, right. So, that will come out to be 0.20 into half, because there is only one child in the family, right, P 01. So, that means only one girl and no boy. So, this the total number of children in the family is 1. So, that probability is 0.20. Then it being a girl or a boy, the probability is the same, therefore, it will be into half. So, that is 0.10, that is the number you enter here. Then similarly, if you want to compute P 02, then it will be 2 children. And so, I am writing the conditional straight away. So, 2 children, probability of that, and then 2 girls given there are 2 children. So, this is 0.35 from here, families having 2 children, that is 0.35, and then 2 girls. So, 1 by 2 into 1 by 2. So, 1 by 4 divided by 4, and so that is 0.0875. So, 0.0875. Then when you want to compute, I have done it here, it is not very this thing, but anyway it is coming up. Maybe I can just show the calculation in a better way. So, when you want to have 0.3, that means all the children are girls. So, this again will be probability 3 children, which is 0.30, then into 1 by 8, because all the 3 are girls. So, 1 by 2 raised to 3, and therefore, you divide by this by 8. So, this is 0.0, then 3 will be 24, then 6, then 8 sevens are 56, and then 40, and 8 fives are 40. So, 0.0375, 0.375. So, when you add up these numbers, this will here will be the probability that x is 0. So, that means, no probability when you pick up a family at random from the community, there are no boys in the family in that family. So, that number will come out to be this, you can add it up. Similarly, this will give you the probability that x is equal to 1, that means one boy in the family, probability x equal to 2, and this will be probability x equal to 3. Okay. And here also you can see that these combinations, and of course, because the boys and girls are equally likely. So, the tables, so once you have computed this part, then this is symmetric, right, because whether having a one boy and 2 girls, or in fact sorry 1 1 when you have 2 children. So, it is whether girl or boy is same, therefore, this will be the same. Then 1 2, see this one we are having, this is 2 0, I am sorry, 0 1 and 1 0. So, that was the number. Then this number, for example, 2 1 and 1 2. 1 2. So, these two numbers. So, this is symmetric, because boys and girls are equally likely. Similarly, here whether all the 3 children in the family are boys or all the 3 children are girls, is the probability must be the, so I am sorry, this should be 0.375. Okay. So, make that correction. So, this will be 0.0375, and then again, as we said, when you add up all these probabilities, they should add up to 1, and here also you will get the marginals. So, this will be probability y equal to 0, probability y equal to 1, probability y equal to 2, and probability y equal to 3. Okay. So, I would like you to complete the tables. I have made some computations for you. So, this is the same. Now, you have to make just these 2 computations, and then you can complete the table. So, this should give you an idea as to how to go about computing joint when the variables are discrete, how to compute the joint distribution function for discrete random variables. So, let us continue with the jointly distributed random variables. Suppose x and y are continuous. So, I will now define another way in the sense that now I will define this through your joint PDF. And so, we are saying that if there exists a function f x comma y, real valued function, which is defined for real x and y, having the property that for every set C, a subset of R 2, that means all pairs of values, the pairs of values which are there in C, then x y belonging to C, that means you see the convention is that the first this is a pair of coordinates, then the first value is for x and the second value is for y. So, then probability that x y belongs to C is this. So, now this is different from the way we define the cumulative distribution function right in the beginning. So, of course, the two will merge to the same thing. So, here the probability should be f x y dx dy. Okay, for a continuously distributed jointly distributed continuous random variable. So, f x y is called the joint PDF of x comma y, and if a and b are two subsets in R square, then probability that x belongs to A and y belongs to B will be integration over A with respect to dx, and actually see what one should make a convention that this must refer to the later one here. So, I should have said this is dy and dx, because just a convention. So, therefore, when you are writing the limits, the ranges, then it is nice to remember that this one refers to the second integral and this is the first. So, the order has to be maintained. So, therefore, this is a b. So, I should have written dy dx of f x comma y. So, the same thing is being sort of repeated, and then for if your f a b as we defined earlier is now x lying between minus infinity and a, y lying between minus infinity and b, then the partial derivatives here delta square delta a delta b f a comma b will be f x y a comma v, right. So, this is the relationship between the cumulative joint cumulative distribution function and joint PDF. Okay. And then of course, the marginal distributions here. So, this will be x belonging to A and y is from minus infinity to infinity. So, in that case you are integrating with respect to y from minus infinity to infinity, and this integral when you are integrating with respect to y will be the marginal. Just as I showed you in the discrete case that you add up for all the possible values of y to get the marginal and the probability of x for a certain value. So, same here, the marginal with respect to x will be you integrate the joint PDF from minus infinity to infinity, and for the marginal of y, the PDF of marginal y, this would be integrating with respect to x from minus infinity to infinity. Okay. And of course, depending on whatever the region of actual definition is. Fine. Now, let us just take up this example. So, if you have this function defined here, which is defined for all values of x from 0 to infinity and for all values of y from 0 to infinity, and it is 0 otherwise. So, it is in the first quadrant that the function is defined, then verify that this is joint PDF. So, therefore, the integral total integral from 0 to infinity and this should be 1, right. So, suppose I just integrate with respect to y first. So, the derivative here the integral is minus e raised to minus y from 0 to infinity, that gives you 1, right, because at infinity this is 0, at 0 this is 1 plus 1. So, then this is this. Now, you integrate with respect to x. So, this is minus 3 upon 3 e raised to minus 3 x going from 0 to infinity, which is equal to 1, right. Now, if you want to compute this particular probability, then your limits will be. So, this time I have taken care of the order. So, this is 2 to infinity for x and for y it is from 0 to 1. And so, again the same integral, you do it with respect to y first, right, take the limits, and then this is 1 minus e raised to minus 1, then you integrate with respect to x, and this will be so the final answer will be this, and so you can go on. So, this is nothing new except that your dimension has increased and the same concepts are there, the same axioms will be followed, and so we will now continue developing this theory and then talk of independent random variables, jointly distributed independent random variables, then we will talk of sum of random variables. So, of course, the thing is that this concept can be extended to more than 2, and except that the writing part is a little tedious, but the same thing will follow. So, I will just revisit this I had shown you this probability, tried to computing this probability. I had drawn the diagram. So, let me just make it more clear, because I had a feeling that I did not do a very good job last time. So, let us see probability x greater than a and y greater than b. Then if this is my origin, this is x equal to a, this is y equal to b, then this is the area that you want to compute the probability on, right. Your region x greater than a, y greater than b is this event represented by this area. So, now we said we will write it as x less than or equal to a. So, x less than or equal to a is this whole area, right, extending on this side, the whole area, and then y less than or equal to b will be this area, right. So, therefore, all this and all this gets covered, and you see that this area, the area that is x less than a, y less than b, okay, this is yeah. So, this portion, because when you are covering x less than a, then it is all of this, y less than b, then it is all this. So, therefore, x less than a, y less than b, this particular area gets covered twice. So, you add here, and therefore, you get this. So, therefore, 1 minus of all this, that means, if I write probability x less than or equal to a plus probability y less than or equal to b minus this, then I will get the region corresponding to this, and therefore, so 1 minus of that, and that will be the probability for this. So, just wanted to revisit this thing, and here also in the other example that we had taken when we were talking of a community in which there are families, and there were probabilities associated with families having no children, 1 child, 2 children and 3 children. So, I thought that though I had asked you to compute, I had computed some probabilities for you, and I asked you to compute the remaining one, but I realized that probably you need a little more working out, and so I thought I will give you the hints here. For example, when you are computing 1 comma 1, then it is the probability 2 children into the conditional probability that it is either a boy girl or girl boy. You see, when you are saying 1 1, so then it can be the first child is boy and the second is girl, or the first child is girl and the second child is a boy. So, therefore, this will be 0.35 into, because the probability of 2 children, families having 2 children is 0.35, then into actually boy girl will be 1/4, because each of them are equally likely, but since there are 2 possible cases. So, 2 into 1/4, therefore, this is half, and so this number comes out to be 1 this is 0.175. Okay. Now, for 1 2, when you want 1 boy and 2 girls, then that means 3 children. So, the probability of having 3 children is 0.3, right. 30% of the families have 3 children. So, this is 0.3. Then the conditional probability of having a boy and 2 girls, and then when with 3 children, having 3 children and then 1 boy and 2 girls. So, now, here again you need to say that, see, it could be the first child who is the boy, other 2 are girls, then it is first girl, then boy, then girl, and girl, girl and boy. So, these 3 possibilities are also there. Therefore, it will become 3/8, right, because each of them is half. So, then when you have these 3 possible cases favorable for your event, then this is 3/8. So, 0.3 into 3/8, that comes out to be 0.1125. Right. And then the rest we had computed, and then these are the marginal. So, that means this I told you is probability x equal to or b equal to 0, right, and probability b equal to 1, probability b equal to 2 and probability b equal to 3. And similarly, here this is the marginal for probability girl, the probability girl is 0, no girl in the family, of course. So, probability there is 1 girl in the family, 2 girls and 3 girls, and then you see that this adds up to 1, because they are marginal PDFs or probability mass functions. And so, once you find out the joint, then you find out the marginals, and then you can do all other computations that are required, the expectation, variance and everything you can compute as we have done it for you. Like even for the joint also you can do it, expectation x y, you will do it, right. And so, you will multiply I think I have given you the expression p x y, this we worked it out, this into your the values that x and y take, right. Y is positive, okay, and so on. Now, I will continue with some more examples of the continuous random variable. So, here let us see, you take a circle of radius r and let us say it is centered at the origin. So, the equation of the circle is x square plus y square equal to r square. So, when you are taking the inside of the circle, then it is less than or equal to r square. So, this is the circle given to you. Then let us, and we just pick a point on inside the circle, then that is a random, because and we are saying that all points are equally likely to be picked up inside the circle. Then x, let x represent the x coordinate of the point that you have picked up, y is the capital Y represents the y coordinate. So, now both x and y are random variables, and since any point in the circle is equally likely, therefore, it will be a constant. The PDF of x comma y, the joint PDF of x comma y will be a constant inside the circle and 0 outside, and this is an example of a two dimensional two variable uniform distribution. Right. So, this represents a uniform distribution, because any point in the region inside and on the circle is equally likely, right. And then now you want to find out the value of c. So, we will have to say that this must integrate to 1 the whole thing, and since this is simply minus infinity to infinity and minus infinity to infinity dx dy, this is an element of area, right. So, when you integrate over the whole of the circle, you will get the area of the circle, okay, by everybody. So, this is you have already done it in your class 12 and so on. So, then c into pi r square is equal to 1, therefore, your constant is 1 upon pi r square, which is expected, right. For in one dimension also, I told you that when you had a uniform random variable, then this was the length of the. So, if this was point A, this was B, then the probability density function for any for this uniform random variable was 1 upon b minus a, which is 1 upon length of the interval in which the random variable is defined. Here the random variable, the pair x comma y is defined inside the circle, and when it is uniformly distributed this pair, then that means that the PDF must be 1 by pi r square, the area of the region. In this case, it is the area of the circle. Okay. Now, you want to compute the marginal of x and marginal PDF of x and marginal PDF of y. So, for x you will integrate from minus infinity to infinity f x y dy, and this is what I want to point out, that. So, your fixed value of x, if you fixed a value of x, then how does your y vary? Y varies along this chord, right, and the length of the chord is, because this length is x, this is r, the radius of the circle. So, this length is under root r square minus x square. So, therefore, this point has the coordinates x comma under root r square minus x square, and this point has coordinates x comma minus under root r square minus x square. So, your y varies from minus under root r square minus x square to under root r square minus x square. So, this is it, right. This reduces, because there is no other mass outside this. So, this is c into dy, and the c is 1 by pi r square. So, this becomes twice under root r square minus x square, and this is defined for all x between minus r and r, right, because your x varies from this point to this point along this, and as your x varies along this, your y varies along this. So, the whole circle gets covered, right. Similarly, because there is symmetry, so your marginal of y will be twice under root r square minus y square upon pi r square, where again y varies. Sorry, this got mixed up. This is minus r less than or equal to y less than or equal to r. Okay, 0 otherwise. Now, suppose you want to find out the distribution of a random variable d, which is the distance of the point from the origin. So, this is under root x square plus y square. So, you take any point here and then this is the distance, the length would be under root of x square plus y square. So, we find out the distribution function of d, which will be f d r. So, that means probability d less than or equal to r. Now, since everything is non-negative, distance is a non-negative number, r is non-negative. So, this event is the same as squaring up both the sides, that means x square plus y square less than or equal to r square, right. The two events are the same. And again by the same argument that for x square plus y square less than or equal to r square. So, all points inside the circle having radius r, all these points will satisfy this define this event, right. Every point inside the circle of radius small r, and therefore, the area here is pi r square, small r square, and divided by the PDF, which is pi r square. So, you can you can do it from by integrating and everything, but this is a straightforward because everything is uniformly distributed. So, therefore, the probability of a point lying inside this circle small r is pi r square, just as we said that the this is the that means, this is the area which is favorable to our event, and then the density of the function is of the two pair is 1 upon pi square r square. So, therefore, the probability the distribution function of d is r square upon capital R square. So, now if you want to find out the PDF of d, the PDF of d would be differentiating this with respect to small r. So, 2 r upon r square and small r varying from 0 to capital R, right, because now d is a non-negative random variable and the value of d will vary from 0 to r, because the point is here, then this way and this way. So, it can go up to capital R. Right. And similarly, you can find out the expectation of d, which will be 2 by 3 r. So, just by geometry helps, you draw pictures, then you can get a good idea as to how to go about solving a problem. So, and the moment you have more than one, if you consider a pair of random variables, and you can see that the complexity will increase the moment you consider higher dimension, that means 3 random variables together, joint density function of 3. But and as I go along, I will try to solve some more problems relating to 2 random variables, joint distributions of 2 random variables. Okay. So, another example on joint distribution of random variables. So, suppose f x y is a function given like this 6 by 7, x square plus x y by 2, x is between 0 and 1 and y is between 0 and 2. So, then you want to verify that this represents a PDF of the variables x y. Okay. So, I just integrate from 0 to 1 and 0 to 2, and the working out shows that okay, this is x square y plus x y square by 2 if you are differentiating with respect to y, because I have written the limits with respect to y first 0 to 2. So, let us integrate with respect to y first, and therefore, this is what you get, and then you look at this, then integration with respect to x 0 to 1. So, that will give you this function, and finally, you get the integral to be equal to 1. So, therefore, the function does represent, because it is a non-negative function, since x and y are both non-negative. So, this is a non-negative function, the integral in the defined in the specified area integrates to 1. So, it represents a PDF. Okay. Now, to compute the marginal or the PDF of x or the marginal of x, you see I have already done it here, because you have to integrate this integral from 0 to 2 dy. So, this integral gives me the marginal of x. So, therefore, this is 2 x square plus x, 0 less than or equal to x less than or equal to 1. And you see that if I now integrate this from 0 to 1, it will give me the answer 1, and hence this is also a PDF. It is non-negative in the specified region, and of course, I should also say 0 otherwise. It is very important that your definition of the PDFs must be complete in the sense that you must specify the region on which it is defined. So, here it is in between x 0 and 1, this is the PDF is defined by this function and it is 0 otherwise. Okay. Then you are asked to compute x greater than y. So, if you have to compute x greater than y, then see I have written down this is the line which represents x equal to y. So, this is the region over which you want to compute this probability, right, because you have to specify the event. So, then it will be see here if you are integrating with respect to x, then you fix your y, that means, right, when I am integrating with respect to x, my x is varying. So, y is fixed. So, when you fix a y in this region, how will your x vary? From y to 1, because this represents 1 here, right, this line. So, that means you are integrating from here to here for a fixed y, and as y changes from 0 to 1, you will cover the whole area, right, like this. So, therefore, range for the variable x is from y to 1 and y varies from 0 to 1. So, this is very important, and again I will keep repeating this, that draw the diagram. In 2 dimensions you can always do it, and then you get a feeling for how what are the ranges of integration and so on. Okay. So, integration with respect to x gives me x square x cube by 3 plus x square y by 4 from y to 1, and that is important because I must integrate with respect to x first, since the limits for x are in terms of y. So, then I will first integrate with respect to x and then get the function as a function of y, and then I integrate with respect to y. So, this has to be the order, and you must keep this in mind. Okay. And so, finally, this comes out to be 15 upon 56. So, the arithmetic should be correct. Now, here what I was saying is that suppose you had to compute the event probability y greater than x. So, in that case you see what will happen is it is this region over which you have to do it. So, then you see you will have to break it up into, or what you can do is okay, maybe no, it is not necessary, because then if y is greater than x, you will want to write the limits for, that means for a given x, how will your y vary? Okay, that is no problem. The y will vary from here to here, that means it will vary from x to 2. So, I will integrate with respect to that means, if y is varying from x to 2. So, we will have to integrate with respect to y here, right. So, the limits would be x to 2 and then x varies from 0 to 1. So, this will be the this will give you this probability, right. If you integrate first with respect to y, x to 2, the same function, and then you integrate with respect to x, right, because for a given x. So, this is how, when you have the diagram, you can immediately see that given a value of x, the corresponding value of y can range from x to 2, and that is it. Yeah, you can compute this way, right. Now, just look at another example, and maybe we do not need to compute it fully, but I will give you an idea here. This is f x y is defined as c into y square minus x square into e raised to minus y. Now, the limits for x are from minus y to y, and y varies from 0 to infinity. So, therefore, to draw the diagram, see what I said is that when y is fixed, then my x is varying from minus y to y. So, it has to be between the lines, this is x equal to y and this is x equal to minus y, right, or minus x equal to y, whatever, whichever way. So, this is this and this is this line. So, your x is in between these two lines and your y varies from 0 to infinity. So, it is this region extending to infinity, right. This is the region, and so once you know this, then there is no problem, because anyway you must first want to find out the value of c. So, find value of c such that this defines a PDF. So, then you can integrate, and you see what will happen is that you come up to here. Now, this is y cube e raised to minus y. So, you will have to do integration by parts, and it will have to be done 3 times, because this will be your first function, this is second. So, you will have to in the first iteration you will get y square, then you will have to do it again to get y, and then get rid of the y. So, therefore, it will be 3 times you will have to repeatedly apply integration by parts to get the value of c. So, that this integral finally has to be equal to 1, and this. Yeah. So, once you have the diagram in front of you, you cannot go wrong. You can always find out the correct limits, and then decide how to like what I was doing is I was dividing the region in a certain way to do the integration, which you have already done in your while you were doing your calculus course. Okay.